So I'd like to first introduce our first speaker. Jeff Siegel is a professor of civil engineering at University of Toronto. He leads the university's Buildings Engineering Research Group. Professor Siegel is an ASHRAE Fellow and a member of the Academy of Fellows of ISEC, the International Society of Indoor Air Quality and Climate. Today, he'll be presenting on the 5 p.m. filtration and air cleaning in homes. Jeff?
Yeah, thanks, Renji, for the introduction, and thanks to the committee for the invitation to speak here. So I'm going to talk today about filtration in residences, and the very first point I want to make is that when we talk about filtration, there's a tendency to talk about the device or the filter. And what I want to do today is really talk about the system and the context in which that exists. And that context really determines everything about filtration performance. And I kind of bin the context into 3 categories. First, of course, you have to get whatever you're trying to remove, in this case, fine PM, to the filter. Then the filter has to remove effectively whatever you're trying to remove. And that removal has to be big enough to compete with other removal processes going on in the environment. So I want to start by talking about airflow. And one of the first things you have to think about is in homes in North America, most systems are recirculating, meaning that they don't have any outside air. They just recirculate air from the building. And if you look at measured recirculation rates, which is the number of house volumes that go through the system when it's operating, you see that there's a wide range. So there's data from 3 investigations, about 70 some homes shown here. And you can see that on one side of this graph, you're getting 2 air changes per hour through a filter. On the other side, you're getting 8 air changes per hour. And so right away, there's going to be a big difference in the performance of any filter depending on this airflow piece. And added to that is this parameter called runtime, which is the fraction of time that the system operates. And the graph I just put up shows data from about 7,000 homes in North America. Each point represents a month of average data with the runtime, or the fraction of the time the system operates, on the y-axis as a function of outdoor temperature. And there's a lot of things you can get from this picture. There's, of course, a lot of variation across these homes. There's some structure with the weather. Systems operate more when it's both colder and hotter, which makes sense. But the really important point here is that red dashed line, which is the median runtime. And it's it's about 18%. And so what that means is you can have the best filter in the world, and over 80% of the time, air is not going through that filter. And so this is kind of step 1 to address. Step 2 is the efficiency of the filter. And I show this curve for a couple of reasons. One is that it's always very comforting to see the kind of familiar U-shaped efficiency curve where smaller particles are removed by Brownian diffusion, bigger particles are removed by inertial mechanisms, and it's usually particles in about the 0.1 to 0.3 micron range where there's a dip. And so this is kind of a classic filter efficiency curve. But the other comment I would make about this is this also shows the dependence of face velocity. And so you can see that at higher face velocities, you get lower removals for small particles in this filter because there's not enough time for Brownian diffusion to happen, and larger removal for particles that are removed by inertia. And so right away, we see the beginnings of how operation might affect filtration performance. Before I show you some real data, it's important to talk about kind of how we test filters. And this is the main data table from ASHRAE standard 52.2, which is one of the common filter standards that's used in the US. And very briefly, this test approach happens in a laboratory. The filter is perfectly installed. It's done at a fixed face velocity or fixed flow rate. The filter is challenged with potassium chloride aerosol, a polydispersed potassium chloride aerosol, and there are successive loadings with an artificial test dust. And both those things will be important in a second. And so you do that, and you figure out the minimum efficiency in each of 3 size ranges, and that tells you the minimum efficiency reporting value, or MERV, for the filter. There's a couple of other things worth mentioning here. One is there's a conditioning step, which can be important for some filters, and I'll talk about that in the context of results in a second. But for the purpose of today, there are kind of 3 really important points. Number 1, this is not a residential standard. It was designed for filters used in commercial buildings, and that kind of introduces some issues. Number 2, this is a laboratory standard, not an in situ standard. And I think that turns out to be one of the most important things we should be talking about today. And number 3, it obviously only addresses 0.3 to 10 micron particles. That's because of the instrumentation that's used to measure particles in the test. And that becomes important, obviously, for things like ultrafine particles. So now let's look at some in situ results from homes. These graphs show 4 different filters, each installed in 20 different homes. And each symbol, shape, and fill is a different home here. And you can see a wide range of particle sizes represented here. And it's a little bit hard to see on some of them, but the black line is the initial efficiency from the laboratory test. The other comment worth mentioning here is the filter in the upper left is a non-electret or a non-charged media filter. And that just is going to be important when we talk about conditioning. So the overall comment you see here for all of these filters is that the given performance in a home can span a very wide range of possible efficiencies. In some cases, some homes are above the efficiency from the lab test. In many cases, they're below, depending on the filter. And so that's important. But really, the big picture here is there is a ton of variation. So simply selecting a filter based on its MERV does not tell you necessarily how that filter will perform in a real home. One of the reasons for that is something called bypass. And so bypass takes many forms. So you can see that sometimes there's a large gap around the filter. Other cases, it's kind of more of a seating gap, a space between the filter and the rack that holds it in place. And a very common thing in some residential buildings is an open filter slot that allows for easy filter changing, but also allows for bypass. And there's some theoretical work on bypass as well as some measurements. And this always has a negative effect on efficiency, but how much depends on the details of the filter and the bypass gap in the system. Another issue is filters change in performance as they age. And in particular, about half of the US market, probably more for higher efficiency residential filters, are electret or charged media filters. And this is some work from Matti Lehtomäki and colleagues from 25 or so years ago, where they showed that the filter performance of this particular electret filter, when it was new, you get those open circles at the top. And when it's charged with different aerosols, so for example, isopropyl alcohol leads to a big decline in performance, as does different amounts of diesel aerosol. And test dust, which is commonly used in filtration test standards, does not mimic the effect of some of these other aerosols. And if we look at how that translates to real buildings, this is the same research group doing work with a filter in a commercial building. And you can see that the gray squares at the top show that when this filter is new, it performs quite well. And as it naturally ages over time, it declines in performance. And by the time it's at 9 months, of use, it's performing much less well than it was when it was new. And Stuart Batterman shared with me some similar data from schools. If we look at how this translates to homes, this shows the PM2.5 filter efficiency for filters that have each been installed for 3 months in homes. The lighter colored bars are the filter efficiency when it's the filter is new, and the darker colored boxes are when the filter is used. And you can see that for the non-charged media, or the regular MERV8 filter, you can see that there's a lot of variation across the homes, which I already showed you, but the median efficiency is the same before and after. Whereas for all of the Electret filters, there is on average a decline in performance over time. And so there's a lot of complication here. It depends on the filter itself, what it's being loaded with, some environmental conditions of how that loading occurs, particularly the relative humidity, but this is a very real effect. So just because you have a MERV filter of a given rating when it's new, it doesn't necessarily perform that way as it ages. And if we put some of these things together, this is data from about 16 studies that show the effectiveness, which is an overall parameter of filtration performance, and for many different types of filters. And you can see that there's not a lot of structure here across all of these investigations. You can have low effectiveness with a relatively highly efficient or high MERV filter, and similarly for a mid or even a low efficiency filter. And so why does this happen? Well, it happens for a lot of reasons, some of which I've already talked about, but it also happens because of the buildings in which the filter is used. So in a leaky building where there's already a lot of removal by ventilation, then you're not going to see as much of an impact of filtration. Another example of the same sort of thing, this is data from 20 homes, and this is the efficiency of 3 filters relative to the efficiency with a MERV8 filter. And this was done with low-cost particle counters, and this is the concentration over 3 months measured every hour in these homes. And what you see here is, again, there's some cases, there's not a lot of pattern with the filter itself, but there's even negative effectivenesses here, which means the concentration was lower with the least efficient MERV8 filter than it was with any of the higher performing filters. And there's a lot of reasons for this. The big ones is this sample of homes had relatively low run times, predominantly older homes that had a lot of leakage and a lot of filter installation and bypass issues as well. But it just goes to show, again, you can't go from what's stamped on the filter to filter performance in real buildings. So in order to have effective filtration, you have to have a good filter. It has to be properly installed. It has to have a big enough flow rate. You have to have a long enough runtime. That filter has to be changed frequently. And of course, the big picture is you have to effectively compete with what else is going on in the building. Now, I've talked about central filters, and others in this session are going to talk about portable air cleaners. But I just wanted to make the overall comment here that all of the same issues apply to portable air cleaners, and there are some other issues having to do with placement, where you get very different effectiveness or very different performance depending on, obviously, the air cleaner itself, but also where it's located relative to sources. And so there are kind of many layers here that you need to do to achieve effective filtration. I would be remiss, especially with what's going on in the world, without talking briefly about other air cleaning technologies. There are many other technologies out there, and in fact, even using the terms that the manufacturers use isn't always helpful because they mean many different things depending on how they're done, and predominantly marketing terms as much as they are scientific or technical terms. However, what we can say based on the literature is that there is, generally speaking, not independent evidence of efficacy or effectiveness in real environments for many of these technologies. Generally speaking, where you see parameters that we can actually evaluate, that we see quite low performance. For some of these technologies or some of these products, there is the potential for harm, predominantly related to ozone emission, byproduct formation, and potentially to ion generation as well. So Dr. Pettenkofer wasn't talking about air cleaners, but I stole a quote from something else he was talking about that I think sums up things quite nicely. So moving forward, I think we want to think about, what research needs do we need to resolve some of this complexity? So I think the big need, given all these contextual issues, is we need some way of assessing in situ filtration performance in homes, potentially with low-cost monitors taking advantage of some of the things that we heard about in the second week of the workshop. And there are some in situ standards out there, particularly an ISO standard, as well as some work in the literature. But I think that we need to think about this idea of how can we actually ensure that filters are performing as they should. And we also really need to think about this question of personal monitoring rather than centralized or some central measure of performance, especially because of spatial issues. You can run into, both from sources as well as from removal, you can run into personal concentrations being very different from room concentrations. And we heard about that earlier in the workshop as well. Another research need is we could probably do a much better job of using technologies well. And I think it's worth thinking about some alternative control approaches, either to maximize performance in the context of energy use. In some cases, there might be electricity reliability or availability issues, as well as kind of preserving filter life because of the economic costs associated with it. And some of these approaches that have been looked at in the literature are things like, a low-cost particle monitor as essentially a thermostat-like control for these devices. But I think we can maybe go further and start thinking about predictive air cleaning. And just as one example of that, we took some of the data from our 20 homes and did a low-cost model and just an unsupervised artificial intelligence model, and identified when is the concentration elevated in this home based on the data that we had measured over the course of the year. And then using a supervised model said, can we predict when that concentration is going to be higher ahead of time? In our case, we were using the data from 2 hours earlier. And an optimal model that weights false negatives and false positives equally was able to predict those high concentration events 2 hours ahead of time, about half the time, a little bit better than that. So we can start thinking about, can we deploy air cleaning resources ahead of when they're going to be most beneficial? And in fact, if we change our model and say, all we care about are minimizing false negatives, we can predict about 90% of those high concentration events ahead of time. And so we can start thinking about these other strategies for controlling pollutants. And the last research need, I think, is we are deploying filters and using filters in many of our buildings, and we have a generally untapped opportunity to understand what exposures those filters have avoided in these environments. So to my knowledge, this is the paper I just put up was the first example of that I've seen in the literature. There are about 60 or 70 articles in the literature that have used this approach of analyzing the dust on filters. And people have shown doing this in a quantitative manner, detailed fingerprints of the concentration of particle-bound contaminants in spaces, including things like OPEs, a class of semi-volatile compounds in homes. You can see things like particle size in homes. And more recently, there's been some work that has shown that we can find things like the SARS-CoV-2 virus on filters. And so we can start using filters as a way of exploring indoor concentrations and the effectiveness of filtration and other control strategies. So to wrap up here, there are a variety of challenges and opportunities with filtration, and the challenges predominantly revolve around effectively using filtration. I think we have to think about that in the context of some of the intervention studies we heard about last week, and making sure that we're actually looking at effective use of interventions and including some of these contextual factors. There are a lot of behavior and communication issues that we'll hear more about later today. I think we also have to think about making sure we're using technologies that work. And then, of course, we should be looking towards better utilization and control, as well as using filters for exposure assessment. And I'll wrap up there. Thank you.
Thank you, Jeff. We're running a little ahead of time, so I'll take the liberty of asking an educational question for some of our audiences. I know that we are from different backgrounds. It's a simple question about what's PM 2.5. Can you define that for us?
Was that for me?
Yeah, for you.
Yeah. So it's the mass of particulate matter less than 2.5 microns in diameter.
Great. And then another question for you. So you noted that the filter efficiency are measured at single pass using ASHRAE 52.2. What's your take on whether the multi-pass used as installed in most cases will reduce or increase the variability in the data shown?
Yeah, so I think, it's a very good question, and I have to give a little bit of a long-winded answer, although I'll keep it brief. I think that the challenge we face is that what the filter loads with affects its performance. And so you run into the situation where every home has a different situation of particles in it and how that filter is used. And so it becomes very hard to make general rules. And of course, the filter matters too. But the short answer I would give is that I do not believe that the deficiency with standard 52.2 revolves around single pass versus multi-pass. I believe that the deficiency is more about the contextual and the use factors.
Great. Well, thank you. We'll bring you back for more questions after we're finished with 2 more presentations. So thank you.